So I casually mentioned humidity and temperature over Coriolis, and we talked about low pressure, high pressure, and rain, and so on. But it's good to understand one of the most basic and one of the most non-linear things in the atmosphere, and that is the relation between temperature and humidity, which also relates to pressure. We'll see later on that the the temperature in the atmosphere is warmest at the surface and decreases to the top of the lower atmosphere, and then other things happen, as we will see. And pressure also decreases, and the relation is given by this. I think you are familiar with enough math now to understand what this means. It's the change in pressure with temperature, and it is related to specific entropy divided by the difference in specific volume between two phases. So we are all obviously talking about water to water vapor, or water vapor to water, and there are other phases as well, of course. Specific entropy, I'm sure you know enough thermodynamics. It's the relation between heating and temperature and how entropy comes out of that. So if you don't know, please look that up. And there is the latent heat associated with the phase change, as well as the specific volume change. So specific entropy is basically per unit entropy per unit mass. Okay, so here P is the pressure, T is temperature, delta S is the difference in specific entropy between the phases, delta V is the difference in specific volume between the two phases, L is the latent heat of the phase change. So if you convert water to water vapor, you have to put energy, so that energy, or if you condense water vapor into water, you're going to release the condensation heat. So that's the latent heat. It is latent. The form most familiar in meteorology related to the phase change between water vapor and liquid water is obtained after some approximations, which we are not going through here, as 1 over ES d ES dt. So change in vapor pressure with respect to temperature as a function of another latent heat of vaporization divided by the gas constant, which I'm sure you are also aware of, times T squared. Okay, here the same equation I've repeated. ES is the saturation vapor pressure of water, LV is the latent heat of vaporization, and RV is the gas constant for water vapor. Okay, a similar relation for the saturation vapor pressure in contact with an ice surface is obtained by replacing the latent heat of vaporization by that of sublimation, which is a process of going directly from ice to water vapor without the melting phase. So that latent heat of vaporization is different. So I hope you understand the latent heat of vaporization is where we are pulling molecules of water out of the water body with winds and temperature difference and humidity difference and so on. So you may have already learned somewhere that the hydrogen bonds in the water are broken, so the molecule escapes to, let's say, into the atmosphere, then energy is lost from the water, so water cools and atmosphere gains that latent heat, and when the water vapor condenses, that is released into the atmosphere, which is very critical for the circulation that we will talk about. Okay, so these equations may be integrated to obtain relationships between saturation vapor pressure and temperature given known values at any point. The most empirically accurate relationships differ slightly from results so obtained. So because of these nonlinearities, we want to have a simpler relation that will give us an estimate of the saturation vapor pressure when the temperature changes. An expression believed accurate to 0.3% for the range of minus 35 degrees centigrade to 35 degrees centigrade is given by Bolden, as where T is temperature in degrees C and vapor pressure is in kilopascal. So vapor pressure is the partial pressure exerted by the water vapor in the air. So you know the Dalton's law of partial pressure. The total pressure is vapor pressure, or the pressure exerted by the vapor and the dry air together, that determines the total pressure. So saturation vapor pressure as a function of temperature is given by this constant and this exponential term, where you have these numbers in the numerator and these numbers in the denominators. I wanted to go through it so that you get an intuitive sense when you look at a figure like this. This is the most critical thing you want to remember in the end. So here we have vapor pressure in hectopascal on this axis and temperature in degrees centigrade on this axis. And the most important thing you want to remember is that this relation is non-linear. It's exponential, as we see here. So as temperature changes, water vapor in the atmosphere changes exponentially, and this is obviously very critical because as we go into climate change, sorry, I'm moving here. Climate change, we are talking about global warming. So the ability of the atmosphere to hold moisture increases exponentially as global warming happens. And then we will see later on that there is a positive feedback, because water vapor is a very strong greenhouse gas, which means if temperature warms, let's say because of CO2 increase or greenhouse gas increases that are not water vapor, then that increased temperature holds more moisture, then more moisture causes more warming because water vapor is also a greenhouse gas. Then you get this positive feedback where increased temperature, increased water vapor, and further increase in temperature. So we are looking at every temperature the saturated vapor pressure, where the air is holding all the moisture it can hold with this relation. So which means to put another molecule of water vapor, you have to condense out a molecule of water vapor that's already in. So you have saturated the air, and then you look at different saturation levels: 75%, 50%, 25%, and so on. So you can bring a air parcel, to saturation either by adding water vapor to it. So let's say at 25 degrees centigrade you have a air parcel at 25% vapor pressure. You can add more vapor to it, water vapor to it, to bring it up to here, or you can cool it. So you can take this air parcel and keep cooling it till you hit saturation. Obviously 25%, 25 degrees doesn't hit saturation till 0 degrees centigrade, so you have to go negative. But if you start here with initial conditions at 50% relative humidity and 21 degrees centigrade, then you can cool it and reach condensation or saturation vapor pressure at 10 degrees centigrade. So dew point temperature in this case is 10 degrees centigrade, because if you cool it, it's going to condense into dew. Okay, so relative humidity here is specific humidity divided by saturation humidity. So at any given temperature, when you say 50% relative humidity, that means it has 50% of the saturation level at that temperature. Okay, at 21 degrees centigrade, the saturation vapor pressure is here, and you are at 50% of that. Okay, so these are simple concepts, but make sure you understand them, because these become very critical, and it's one of the most nonlinear things in the atmosphere in terms of water vapor condensation, cloud formation, rainfall happening, energy getting released by condensation, and driving the circulation. So the diabatic heating or adiabatic heating, depending on the processes, is what drives the circulation by creating pressure gradient with that relation between pressure and temperature that we saw, and so on. So I wanted to include this here so that when we come back to later on to talk about temperature and water vapor, you have this in mind. Okay, so just remember that nice nonlinear relation between temperature and vapor pressure, and this is what is the famous Clausius Clapeyron relation. There are many details we'll come to when we talk about climate change and global warming, because the key question then is how much water vapor increase happens with each degree of warming, and what that means in terms of the increase in rainfall. You think increasing water vapor in the atmosphere leads to more rainfall, but there is obviously a lot of other things involved, like the circulation and where the evaporation is happening, where that moisture is being carried, and where it is raining. So then it'll become a question of whether dry regions will get more rain because of global warming or less rain. Will wet regions get more rain or less rain, and how the rain will change. Will it change uniformly, or so you have to always look at frequency, duration, and the intensity of rainfall. So this relation, that's why, is very critical, and we will look at it more and more as we go along. Okay.